So here we're going to finish talking about dry deposition and wet deposition, just so we can do maybe a little more interesting problem in class. So we started talking about dry deposition. We talked about impaction and how that can be important for taking particles out of air, because air can go around things that particles just aren't able to, so they kind of crash into them and get removed from the atmosphere. And that's very challenging to model, so we don't really worry about it here. And we also started to talk about particle deposition. So the first part of that is trying to figure out how quickly something settles out of the atmosphere. So we can use this modified version of Stokes' law, which remember we also used when we were talking about things settling out of water. It's the same idea, but here we're using air. So we can calculate the settling velocity, and we did some examples of that in class. So that's part of the story. The other thing we might want to know is how quickly something settles out of the air, which we're calling, same as we've called for other things, we're calling that a flux density. So that is the mass of particles landing on a square area of the surface of the Earth per given time. And to do that, we need the deposition velocity, here, distance per time, how quickly something falls out of the air, and the concentration of those particles in the air. And as you may have guessed, we can use the settling velocity as the deposition velocity, and we'll do that in class. Okay, so here is an example of how to calculate the flux density that I will have a separate video showing you how to do that. But this is the example we'll use, looking at how quickly sulfate aerosol deposits onto the surface. Okay, so wet deposition really is even a little bit more simple than dry deposition. So it's the absorption of pollutants, particles or gases, into liquid droplets or ice crystals. So there are two terms that people sort of use. One is rain out. So that's rain droplets forming clouds, and the droplets dissolve or absorb atmospheric chemicals or particles as they condense. So that's sort of what defines that differently than washout. So washout is when gases, vapors, or particles are absorbed by a raindrop after it starts falling. So it's not in the cloud. This is kind of what that raindrop absorbs as it's on its way down from the cloud to the ground. So those are the two big terms. And our equation for wet deposition looks a lot like the equation for dry deposition. Again, we're calculating the flux density, J, of wet deposition, so the mass of chemical arriving on the surface of the Earth in a given area of the surface per unit time. And to know that, we need to know the concentration of the chemical in the water, in rain, and the rainfall rate. So we may not have the information about the concentration of a chemical in water. We might actually have more information on how much is in the air. So what we have to do is rearrange Henry's law constant so that the concentration of water is on one side, and then we substitute H and the concentration in the air into this equation. So I will derive that in a separate video. It'll be a really short video. If you want to see me do that, I will do that in a separate little video. And here again, we're using the unitless H. Okay, so here is the basic equation, and here we were using this I over H, or this 1 over H. You could think of this as the concentration of the chemical in air times 1 over H times I. And in the air pollution field, this 1 over H term is often called the washout ratio. And then that is what is tabulated. So these values, each of these values is 1 over H, but in the field they usually call that the washout ratio. So you can look that up, simply because it's the inverse of Henry's law constant, essentially, and put that into your equation. So if you know the concentration of the chemical in the air, you can look up the washout ratio, and then if you know the average rate of rainfall, then you can figure out how much is going to land on the ground in wet deposition. And here is the example that we will do in a separate video. And just to kind of show you what that might look like a little bit. So this is the ambient air concentration of mercury in Vermont. We know it's about this, and we know that Burlington gets about 0.762 meters of rain per year. And then we know we're talking about mercury, so we can just look up that value for the washout ratio in a table and then put all those values in and calculate J. And this is just showing you the washout ratios for particles. So things like radioactive fallout, organic dust, pollen, lead, and zinc. So back here we were looking at for gases and vapors. Here we're talking about particles. Okay, so just to kind of sum up, we've got the primary mechanisms of removal of things from the atmosphere being dry deposition, and we use Stokes' law to estimate sort of settling time or settling velocity. And then we can estimate the flux. And in case you missed it, this is essentially a fixed law, what we're using right off the bat in class with surface water. And wet deposition, we've got rainout and washout. And again, this is just a modified fixed law that uses washout ratio to estimate flux. And that's it. The next little bit of the last bit that we'll be talking about in class and I think one more video are chemical reactions. So again, thanks for watching.